So as usual, I request, to those who can turn on their videos, please do so. Again, not mandatory. Yeah. Okay. All right. So let's begin this, last lecture of this course. Um, Glad that all of you have managed to, run this far. Even if we are a tiny group, I think we stayed strong. So, thanks to all of you. Um, so today we will actually continue our investigation into these related algorithmic models, related class of algorithms. And so last time, we saw a specific model as an example. We saw this so-called spectral algorithms, and we stated a theorem that somehow says that for some reasonable class of average case problems, spectral algorithms turn out to be essentially just as powerful for solving distinguishing problems on those distributions, right? That's basically what we saw. Let's maybe describe it in somewhat more detail. So we had last time we kind of categorized the average case problems into maybe three broad categories. We said, hey, an average case problem is um, specified by giving a distribution or instances. And, we can broadly think of two kinds of distributions. So, we can define the so-called planted distribution. And the property of a planted distribution is that it is supported on yes instances, or instances, where every instance, or let's say with high probability, most instances have a solution. So these are, yes instances. By the way, my screen is visible, right? Like you all can see my
Uh,
screen and you all can see where I'm writing.
It's
Okay, good.
not getting
uh,
updated.
yeah, the it just says the title at the top, but we're not getting the
Yeah.
new stuff.
Oh, that's bad. Well, thanks for finding out. All right, let's see. Let's try again. How about now?
Yeah.
Okay, good.
We, we can see the
Um,
current screen now. Yeah.
you can see what?
We can see the current screen. We don't know if it's going to get updated or not. Yeah, it's scrolling. It's
Yeah, yeah, yes. This is it. This is as good
yeah,
as it gets, Praneeth. It's not going to get better than this.
yeah.
Okay, so we have average case problems are specified by giving distributions over problem instances, and we saw two kinds of distributions which are relevant for us. One of them we call the planted distribution, and this was basically a distribution over instances of a problem, which are soluble, all of which have a solution, or at least most of which have a solution. And we also define the related null model, where with high probability no instance has a solution, right? And then given instances drawn from deplanted or denull, we could define three kinds of problems, right? We could define, for the planted distribution, the natural question to ask is, well, find the planted solution. And for the null distribution, the natural question we could ask is, well, refute the existence of a solution, prove that the instance is unsatisfiable. And then there was a third category of problems, the distinguishing problems, and that was, given an instance, let's call it G, which is chosen either according to deplanted or according to denull, uh, you know, um, report correctly what distribution generated it. And this can be thought of as a distinguishing problem because you're trying to distinguish the distribution that generated the instance, right? Good. Um, I think one thing to notice is that the distinguishing problem is easier than both planted and the refutation problem. Okay, so why is it true? Well, if you have a, let's say, a refutation algorithm, then you simply run it on instance. If it succeeds in refuting, then you have a proof that the instance is unsatisfiable, and then you can safely report that the distribution was denull. If not, you can safely report that the distribution is deplanted, and you will succeed with like 1 minus little of 1 probability here, the little of 1 coming from the failure, let's say, of your refutation algorithm. It's not gonna always output a reasonable answer. It's always like whenever it says unsatisfiable or refuted, it is correct, but it may not refute every instance which is unsatisfiable. But regardless of that, with 1 minus little of 1 probability, you will succeed, right? Similarly, if you have an algorithm for solving a planted problem, you can solve the distinguishing problem using it, because you will simply run that algorithm on an instance drawn according to the planted distribution. You would discover an assignment or discover a solution, and assuming that you can easily check solutions, which implicitly we are here, we can confirm to ourselves that the instance was truly generated from the planted distribution this way, right? So both algorithms for either the planted distribution, either solving the search problem in the context of planted sorry, 1 second. Okay. All right, yeah, so both where is it? Yeah, sorry, Misha, I just observed. Also, feel free to make such messages public, because Peter is not around, so it's up to me to pay attention. Anyhow, yeah. So good. So hopefully Anubhav's here, and you didn't miss a lot. I'm basically pontificating as usual. So it should all be good. Okay, good. So I guess the point I was making, Anubhav, before you joined, was that we defined the three kinds of distributions. Well, two kinds of distributions: planted and null. Planted distribution, is supported essentially on instances of a problem which are soluble. The null distribution is supported on instances of the problem which are insoluble. And then the question you ask about the null distribution is to find a refutation efficiently. For the planted distribution, you naturally ask the question of finding the planted solution efficiently. And then there's a third kind of problem, which is given an instance which is generated according to one of the two distributions, you've got to tell me which distribution generated it, right? And this can be sort of a distinguishing problem. You're trying to distinguish between the two distributions that generated the instance by looking at the instance. And the point I was trying to make is, that if you have a algorithm to solve either of the planted or refutation problems, then you can in fact solve the distinguishing problem using it. And there is a straightforward way to do that, and so that's basically the reason for the statement. Distinguishing is easier than both planted and refutation. Um, that's good, very good. So today, so last time what did we do? Well, we discussed well, we kind of discussed algorithms for all three kinds of problems. But you could view them in specifically as algorithms for solving the distinguishing problem, because in some sense then we don't have to worry whether we invented a algorithm to solve the planted problem or the refutation problem, right? And so last time we saw this example of an algorithm of a class of algorithms called as spectral algorithms that involve building some cleverly chosen matrices out of the input data, and then computing the largest eigenvalue of it, and using the eigenvalue to somehow distinguish between planted and null distributions. You can also use it to refute, in fact, and we saw some of the examples, right? So today we will study yet another special class of algorithms, and these will be low degree polynomial. I'll explain what that means in this context in a second. But you can call these algorithms the low degree polynomial algorithms, and they are naturally seen as algorithms for solving the distinguishing problems. They are certainly not an algorithm that can be reasonably applied to solve the refutation problem. There is a way to think about this algorithms as also solving the planted problem, but that's again somewhat of a stretch, and there is it's kind of yeah, it's much less well developed. So we'll think of this algorithmic class as applied only to this third, the distinguishing problem today. Okay,
Professor, I
very
think
good.
Cheers.
your screen is not updating.
Oh man. Okay. Um, yeah, I don't know. I'm just gonna use AirPlay again now. Let's see. Okay. Now is my screen visible? Come on.
It says you have started screen sharing, but that's
Ah, there we
okay.
are.
I think yes.
Okay. Well, Zoom is trying to show us what all could have gone wrong in the early parts of the semester. It's just giving us examples of new ways it can fail. Anyway, all right. So good. So today we'll talk about this. Different class of algorithms. You'll see, in fact, that in some sense they can be seen as something very related to, but simpler than spectral algorithms. And I think the point I was making just before we got interrupted was that they are naturally thought of as algorithms for solving the distinguishing problem. Okay, good. So just like last time, we will work with the same two examples. So I want to remind you of the setting that we discussed the last time. The first problem we saw was the click problem, the max click problem in random graphs. And just to remind you what the distributions are, the d null here was simply the Erdős-Rényi distribution, where you choose a graph on n vertices where every edge is present independently with probability half. Okay, and deplanted is basically the distribution that is obtained by drawing a graph from g and half, choosing some omega vertices at random, let's say, and then completing the click on them. So I'm just going to call this distribution g and half plus omega click. Okay, that's all I call them. And you can define all three problems that we talked about earlier on these two distributions. The other example to keep in mind, and I'll play with this example also a lot today, is random constraint satisfaction, in particular random 3 XOR problem. Again, you could describe like literally hundreds of problems of this kind, which are both interesting and well studied, but we've got to choose the simplest so that we can make the conceptual point we're after. So we'll study only these two examples again today. Okay, and so let's maybe clarify what the distribution d null and d planted is. And today, with an eye for something that I want to do later on, I want to describe a slightly different distribution for random 3 XOR. Well, it's kind of the same, but I'm going to describe it slightly differently today. Okay. So if you remember, the random 3 XOR problem is specified by so there are some parameters, n, which is the number of variables, m, which is the number of constraints, and once I've chosen n and m, then in order to describe, let's say for example, a random 3 XOR formula, you need to tell me which triples are included in constraints. Okay, and we can describe these triples which are included in constraints by means of some m edge 3 uniform hypergraph, right, which is basically simply the collection of triples that appear as constraints. Okay, and then for each triple I have to choose a right hand side, right, because the 3 XOR constraint looks like xi, xj, xk equals bijk, right? So the second choice I need to make is what are the right hand sides for each constraint. Okay, now in order to make the point I want to later, and perhaps also to make the point that there are several distributions which are interesting for the same problem, today I'm going to look at the distribution where the hypergraph H is fixed. Okay, so for both d planted and d null, we're going to think of like some fixed m edge 3 uniform hypergraph on n variables. Okay, the only difference between planted distribution and the null distribution would be how the right hand sides are chosen. Okay, so I'm going to call the edges of the hypergraph, which are fixed once and for all, as C1, C2, Cm. Okay. And these, remember, are just, triples. So they are like elements of n choose 3. Good. And I have not told you how I chose this. We're going to assume they are fixed for now. And then, as we build on, I'll tell you, how these CIs are generated. The B1, B2, Bm are the only part of the data which is going to be random. Okay. And I'm going to describe two different distributions of generating these at random. Okay. So in dplanted, well, actually, let's describe d null first. The d null distribution would simply be, choose each bi independently as a random bit. Okay, that's d null. My 2-column format, just like every conference paper that you submit in 2-column format, is really not serving me well. You can see the downside of 2-column format right here. So we're gonna, drop it right here. Unlike ACM, we don't have to answer to anyone. So the planted distribution, remember the planted distribution has to somehow generate a satisfiable, 3 XOR formula. And so the way I'm going to do this is by first picking an assignment x star in plus minus 1 to the n uniformly at random. Okay. And then for each for each CI, set BI to be XCI star, which is basically, the product of the bits of x star which lie in C sub I. Okay. Now notice that by design, in the planted distribution, x star satisfies all the constraints that I have so generated. In fact, that is the reason I'm choosing the distribution this way. Okay. Notice also that the amount of randomness in the right-hand side, the list of right-hand sides in the planted distribution is only n bits, right? Because the only random choice I made is x star. But remember, we always think of m as much bigger than n. And so in the null distribution, there is a lot more randomness, right? All the m right-hand sides are uniformly at random. So there is m bits of randomness, in the null distribution. In the planted distribution, only n bits of randomness. And we are going to think of settings where m is much bigger than n. So some big constant times n at the very least. In fact, if you remember, we use these kind of bounds. And so, one difference in the null and the planted distribution right away, in addition to, planted being basically always satisfiable, is that, the amount of randomness in the two distributions is very, very different. Okay. And now, you can again use the same Chernoff plus union bound type argument to prove that as long as, m is bigger than, let's say, this number c n over epsilon square for some large enough constant c bigger than 0, no more than half plus epsilon fraction of the constraints of the null distribution can be satisfied with some, let's say 99% probability. Okay. Again, I'm sure you believe this. You're not like surprised at this assertion. So I'm not going to, go into details of it. But that's it. Okay. Those are the two problems I'll play with today. Okay. So just keep them in mind. Keep this particular, setup in mind. Very good. So now that, we've discussed two example problems, it's time to define what the low degree polynomial model actually allows you to do. So, as I said, it's a restricted class of algorithms. So, it's going to allow you to solve the problem of distinguishing between planted and null distributions, by applying only certain kinds of algorithms. You're not free to allow, you're not free to use any Turing machine which runs in polynomial time. You only have to, somehow use a specific class of algorithms. Let's describe which class of algorithms. Okay. So, well, if you think about it, how does the distinguishing algorithm work? Well, it takes, let's call script A, as our algorithm. Then, it takes an instance G, and it's supposed to output planted or null. So this value, let's say, is without loss of generality in 0, 1. And you can think of 0 as, some assertion that I am, call it null, no solution. 1, let's call it, the assertion that the algorithm thinks the distribution is planted. And we would like the algorithm to be right most of the time. So we'll say, correctness property of a distinguishing algorithm is that, probability g n half, or more generally, g drawn from d null, um, a of g is 0, is 1 minus little o of 1. And, this n is our parameter, asymptotic parameter here. G drawn from D planted. A of G is 1, is, 1 minus little o of 1. Again, think of some growing parameter as the input size or whatever, okay? So that's our connectors guarantee of any algorithm. Now, what does a low degree algorithm mean? Well, low degree polynomial algorithm can only compute low degree polynomial functions of data, okay? So A of G must be, so let's in fact, now use an extra parameter. Let's call it degree D polynomial algorithm. Must be a degree D polynomial in G. Now, let's clarify what does in G mean, okay? Because what does it mean to compute polynomials and inputs, okay? Now, you would see that, this is somewhat representation specific, okay? But we're going to allow ourselves the freedom to do that, okay? But, you should remember that whenever you look at an algorithmic model, one of the things you should be asking is, is it representation? How tied is it to the input representation? Now, this particular model is somewhat tied down to the representation. For good, for better or for worse, that's what it is, okay? So what does A of G must be a degree D polynomial in G mean? It kind of means, something relevant, something natural that you might imagine. So, G can be represented as an element. So, for example, so I can only in some sense describe it by means of an example here. So, in the context of click, G can be thought of as an element of 0, 1 to the n choose 2, where, basically each coordinate tells you whether, so each coordinate kind of labels one of the n choose 2 possible edges of an n vertex graph. And then, 0, 1 to the n choose 2 gives you an indicator vector of which edges were, somehow present, okay, in the graph. So G can be thought of as just an element of 0, 1 to the n choose 2. And then, it's described by n choose 2 different variables. You can think of them as like edge indicator variables. There are 0, 1 variables for every edge. And, in this case, A of G can only compute low degree polynomials, degree D polynomials, in over 0, 1 to the n choose 2, where the graph is seen as an element of, this domain, okay? Similarly, in the context of, let's say, for example, 3XOR, you saw, here that the right-hand sides were B1, B2, Bm. So the right-hand sides, let's call them B bar, were, elements of plus minus 1 to the m, right? Because remember, we fixed the we fixed the hypergraph once and for all. This is the reason I can think of the domain as nicely, again, a hypercube. By the way, this is the reason I chose that, this simplifies my notation and description, etc. So, in 3XOR, the input is simply just the right-hand side vector, which is like a vector of m bits. You're thinking of bits as plus minus 1 in this context. And so, B bar, again, in this case, A of B bar, for example, can compute any degree D polynomial over, plus minus 1 to the m. Good. Are there any questions about, what I'm allowing you to do in this algorithmic model? It might look like a completely bogus model, by the way. It's like, you might have several questions. Why is this model interesting? Why should I study it? Why is it so representation specific? Why is it interesting, etc.? We'll try to answer some of these questions, okay? But at least is the framework, is the setup clear? Is the meaning of low degree polynomial algorithms clear, at least in the two examples we saw? Good, very good. Okay, so, you understand at least somewhat what a low degree polynomial algorithm might mean. And so today I want to, for whatever reason, well, some of them might become clear, in half an hour time, but To begin with, we'll just investigate how powerful are, these algorithms for solving the distinguishing problem. Okay. So let's look at the, example we had, the click problem. So in the click problem, if you wanted to distinguish between, um, planted and null distributions, what kind of distinguishers can you think of? So, last time we saw the spectral algorithms, but, let's brainstorm a little bit. Can someone tell me, some suggestions for distinguishing between graphs which are, chosen from G and half versus graphs which are chosen from G and half plus a random omega size planted click?
Run sum of squares.
Run sum of squares is indeed a very good, choice of algorithms. But let's, go simpler. You don't know semi-definite programs. Somebody didn't even teach you linear programs. I mean, they did a horrible job educating you if that's what is a situation. But let's say you have not learned of LPs, you haven't learned SDPs. What would you do? I gave you two graphs, or I gave you two possible distributions, and I gave you a graph. What would you check about the graph in order to somehow determine if it has a large click inside it? So, let me start you off, right? One thing you could do, for example, is think that, hey, you know what? If I add a large click to a graph, I'm going to, blow up the number of edges in it, right? I'm going to increase the number of edges in the graph. So maybe um, one thing I can check is number of edges of G bigger than some threshold. I don't know what threshold to choose, but I can just think of the algorithm that computes the number of edges in the graph, sees if it is larger than some number. If it is larger, maybe it outputs that, it is chosen from the planted distribution. And if it is smaller than the threshold, it would just, output that it doesn't have a click. It's probably chosen from the null distribution. Okay. Now, if you want to analyze such algorithms, I'm not going to formally analyze such algorithms, but just to, give you a sense of what these kind of algorithms do. Well, one thing you could, how do you analyze this? Well, let's look at the distribution of edges of G, and it's a random variable, right? But the distribution of edges in G and half is, has a mean n choose 2 by 2, because every edge is chosen, with probability half to be inside the graph. And, there is a standard deviation, which is like O of n, right? And so I'm going to think of the distribution as specified by a mean and its standard deviation, okay? Because we are thinking heuristically, this is how we'll think about it. So, the statistic, the number of edges, is a random variable or a statistic of the graph. And, it basically looks like its mean, which is half n choose 2, plus some O of n, which is a standard deviation, okay? Now think of this as, some number like b times n, okay? If I wanted, for example, a bound on the number of edges that holds with, let's say, probability 1 minus 1 over n, what should I choose b to be? B to be, b would roughly be root log n if you want to apply, let's say, Chernoff bounds, okay? Again, we'll take it for face value if this calculation is not clear, but it's relatively simple, Chernoff bound argument that if I choose, for example, b to be, some order root log n, then, the number of edges in, G chosen from G and half is at most some half n choose 2 plus order root log n, with probability at least, let's say, 1 minus 1 over n. Okay. So now, one could ask, for what omega is, the number of edges in G chosen from G and half plus omega click is bigger than, this number, right? That's when you would succeed, right? So now, roughly speaking, the number of edges in G and half is about n choose 2 half, at least the mean of it. And then, the omega click adds roughly omega choose 2 edges. And because we are not really worried about constant factors in omega, we can think of this as omega square, right? And so in order to somehow defeat this order root log n times n factor, I would have to choose omega square bigger than n root log n or whatever. And that's going to give me, omega, which is bigger than some root n times, log n to the 1/4. I hope I did this calculation right, but that's what you're getting. Okay. And so, it's worse in terms of a distinguishing algorithm than the spectral algorithm we saw earlier, but it's, doing something, right? And notice in particular here that the number of edges is a linear polynomial in, the representation of G as an element of 0, 1 to the n choose 2. And so, this linear polynomial distinguisher is, is not great. It's not, achieving the kind of guarantees we saw earlier, but it's not so bad either, right? It's reasonable. There is a variant of this distinguisher, which, simply computes the maximum degree of any vertex. Okay, instead of computing the number of edges, compute, what's the degree of the maximum degree vertex in it. Okay. And, again, you can choose what threshold, etc., are, things to decide. And you can, again, get some algorithm that works with like root n up to polylog factors or like log n, some polynomial in log n factors. Okay. So, we saw two distinguishers. One was, number of edges. The other is maximum degree. Both of them are natural. Both of them look simple, right? Is the second distinguisher a low degree polynomial distinguisher? The first one was a linear polynomial. We were simply computing the value of a linear polynomial. What about, the max degree? So the maximum degree is a function of G as an element of 0, 1 to the n choose 2, right? As a function of 0, 1 to the n choose 2, is it a low degree polynomial? Or what is the degree of max degree as a polynomial of G?
N choose 2.
Exactly.
Something.
It is indeed. I don't know. I don't exactly know if it is. Okay, let me think about it. I mean, any function of 0, 1 to the n choose 2 is a polynomial of degree at most n choose 2. That's certainly an upper bound. And without spending too much time on it, it's likely also a tight upper bound. As in, you can't do much better. Um, much better than the trivial upper bound for expressing max degree as a polynomial function. So it seems like polynomial functions are really bogus, right? Like they cannot even compute this max degree function, which is a relatively simple thing that you can do with a graph, right? You can look at the graph, calculate degrees of vertices, and find out the maximum degree. Okay. But there is one trick that we'll use again and again that shows that you can basically approximate the performance of max degree with a polynomial up to basically any reasonable sense that you might actually need. And that's one of the reasons why like polynomials are not so bad, even though these simple functions are not expressible as polynomials. So let me tell you this trick, okay? And so I'm going to call it the LP L infinity trick because it's a very simple and very general trick, okay? And it relies on approximating the max norm of a vector by its LP norm, if you know what that is. Okay. And so if you look at the max degree, you look at the vector of degrees of so this is vector of degrees, and max degree is the L infinity norm of this vector, right? So instead of the L infinity norm, consider the following function. Let's maybe f sub t of g as some di to the t. Okay, think of t as some integer, large integer, and think of the function some I di to the t. What is the degree of ft of g as a function of the graph?
T.
Right. So in particular, this is a polynomial of degree t, right? Okay. So now let's try to understand, how this function may at all be related to, the max degree, which is what we care about, right? So notice that ft of g is always bigger than d max to the t, simply because d max is an element of d1. Well, d max is an element of the set d1 through dn, right? And it's clearly at most n times d max to the t, right? So now let's try to understand. Suppose that with probability 1 minus little o of 1 ft of g over g, let's say from the null distribution, ft of g oh sorry, d max of g happens to be some number. So actually we computed that number, root n, let's say root log n. Okay, while with probability 1, d max of g chosen from gn half plus omega click, d max of g is bigger than omega plus n over 2. That's suppose, yeah, that's about right. But okay, again, like don't pay too much attention to these thresholds. The point I'm trying to make, I guess, is that well, what am I trying to pay attention to here? Actually, okay. This is not good for my point, but maybe I should actually subtract off d minus n over 2, the mean, and then take powers. It is still a degree t polynomial. Okay. Now, okay, so now notice that d max of g minus the mean n over 2 is at most some order root log n whatever times n root n, because the deviation of the degree of any vertex is like root n, and then by union bound no degree exceeds order root log n times root n, okay, by the same kind of stuff that we were discussing earlier. On the other hand, when there is an omega size slanted click, then for the vertices that lie in the click, the degree gets a bump by plus omega because they are connected to every vertex in the click. And so d max, the same statistic, d max minus n over 2 is bigger than omega. Okay. And so now what? So the point is that if omega is, let's say, much bigger than much bigger than so let's call this b root n, where b is order root log n. So b is some chosen threshold. So now imagine that omega is bigger than 2 times b times root n. So basically twice as much as the threshold that you used in here. Okay. So then what? Well, in that case, notice that if you now, so so I guess what I'm saying is that this particular statistic is a factor 2 different in the planted distribution compared to the null distribution. Okay. So now let's try to understand what happens to this ft of g statistic. So ft of g in g and half would basically look like di minus n over 2 to the t, which is at most b to the t root n to the t. Okay, while ft of g, so this is null, and in the planted case, ft of g would look like some di minus n over 2 to the t, which is bigger than omega to the t, which is at least 2b root n to the t. Okay, I guess all I the reason I did all of this thing is to basically notice that these two numbers are now different by a factor 2 to the t. Okay, so now sorry, did I do that correct? Oh, there should be an n here because I'm summing up n numbers. And so now the point is that 2 to the t b to the t root n to the t dominates n times b to the t root n to the t whenever 2 to the t is bigger than n or t is bigger than log n. Okay, so what have we learned? That instead of the max degree, so conclusion, instead of d max or d max minus n over 2, we could have simply considered ft of g for t which is like log n. Okay, and ft of g has basically the same distinguishing power, at least if you don't care about the constant factors, as the d max minus n over 2 statistic. Okay, so that's good. So we actually were able to replicate this d max performance with a log n degree polynomial. So now the big question: should log n degree polynomials be considered efficient? So, whenever we define an algorithmic model, we must first ask ourselves, what is an efficient algorithm in this model, right? Now, let's think about that question for a second. If you think of low degree polynomials as an algorithmic model, then, given a polynomial, which is basically the algorithm itself now, you must think of, the running time required to compute that polynomial over the input, right? So how long does it take to compute a degree t polynomial in G? So what is the running time required if I give you nothing, if I gave you the degree t polynomial to compute on G? How long does it take you to do that?
N to the t.
N to the t, you mean?
Yeah.
Okay, yeah, n to the t is right, or actually n to the 2t roughly, or at least n to the O of t is definitely right, because G is represented as an n square thing. So you just compute all possible monomials. You think of each monomial taking some fixed constant amount of time if you were given the graph as an adjacency matrix input, and good. So implicitly, I want to remind that Tim used the representation of a polynomial in the coefficient. Like you assumed here that the polynomial is given to you. The polynomial that describes the algorithm is given to you by describing each of its coefficients. So here we assumed that the polynomial is described as a vector of its coefficients. Which, if I tell you nothing, then in some sense it's the only representation that you can think of in the context of describing degree t polynomials. But it turns out that in many cases you can have some implicit descriptions that can allow you to compute polynomials faster. We won't go into it, but there are some general results which for a large class of polynomials allow you to compute, for example, degree t polynomials in 2 to the O of t poly n time instead of n to the O of t. And that's kind of nice because when t is log n, this is still polynomial while n to the O of t is not. But again, I'm not going to describe this technique to you or discuss what these polynomials are. They're kind of relevant in the context of clique and related problems, but again, does not matter. I think the message of this discussion is that I am going to think of log n as efficient for today's purposes. Okay, so we're going to think. So whether you buy this shady argument or not, we'll think of degree order log n polynomials as efficient algorithms, just for heuristic purposes. Now, in the context of clique problem, this is especially bogus because there is a trivial algorithm that solves the problem in n to the O of log n time. Okay, but don't worry about it right now. We are the clique is only an example here, and we are trying to maybe study the model somewhat more generally. It is true that it is basically stupid when you think of the clique problem, but we'll soon discuss what it means in the context of this 3 XOR problem. But anyway, the message of so far what we've done is that even this d max, the degree max statistic that we was thinking, even though it looks like it would be it would not be easy to express it as a polynomial, its performance can be replicated by a order log n degree polynomial to to a reasonable degree of accuracy, which means that it in some sense is captured by low degree polynomials. Okay, good. But we should go back to this algorithm that we studied the last time. So we studied a different algorithm, a different distinguisher, for again the clique problem. And what was that distinguisher? It was lambda max, the largest eigenvalue of the plus minus 1 adjacency matrix of the graph. And if you recall, we proved that lambda max of G is order root n. So when G is drawn from G in half over with probability, let's say 1 minus the law of 1 over G from the null distribution. And so we in fact use this to conclude that if omega, if omega is bigger than some c root n for c large enough, then lambda max of G is a distinguisher. Right? Still following? Again, feel free to stop me. Okay, this is the last class. What am I going to do? So good. So so lambda max of G is a distinguisher. Very good. And we can ask the same question. This looks like it's doing some non-trivial computation, right? It's computing the eigenvalue of a matrix. Is it a low degree polynomial? Well, it's not, right? And I hope you see that there is no reason for why the largest eigenvalue of a matrix, whose entries are degree 1 polynomials of the input, has to be a low degree polynomial at all. In some sense, there is no reason for it, right? Like it's not a polynomial function. Eigenvalues, and especially the largest eigenvalue, is not a polynomial function at all. But we will do the same L infinity LP trick here, and make it a polynomial, and we will be able to derive exactly the same conclusion, that a degree log n polynomial can simulate the performance of lambda max A of G. Okay, so here is a fact towards that. So the fact is that suppose A is a symmetric n by n matrix. Let's say its eigenvalues are lambda 1 to lambda 1. Let's say they're arranged in increasing order. So let's maybe write it a bit more clearly. Okay, then the eigenvalues of a to the k are, I'm sure that this might have been a question on homework 0. So can someone tell me what the eigenvalues of a to the k are?
K powers of the eigenvalues of A.
Exactly. So they are lambda 1 to the k, so on up to lambda n to the k. Okay. That's very good. Actually, let's think of k as always being even so that we don't run into the sign issues, and think of this order as really order on, um, magnitudes of lambda i's so that we don't have to worry about the sign issues. You'll see in some sense that this is actually a non-trivial issue, and I'll come back to it later on. But let's continue for now. Okay. Good. So now then, because of the order I chose, I can write this. Very good. So then what? So then, well, I guess this is the fact continued. Then, in particular, as a consequence, some lambda I to the 2k is a degree 2k polynomial in entries of A. So, okay, who wants to tell me the proof of this fact? Like in some sense, I did the proof in the statement of the fact itself, but I want someone to point out to me the one remaining piece that allows me to conclude that the sum of 2kth powers of the eigenvalues of A is in fact a degree 2k polynomial in the entries of A.
Trace of
Trace of
A to the
Do that again. Choose a random second of the minute to start, and so that you don't
It's
collide.
the trace of A to the 2k.
Okay, yeah, Praneet won the competition here. The observation is that trace of a to the 2k is this quantity, and well, I guess there is one more point to make to complete the logical loop. Praneet, you want to do that? So trace of a to the 2k is a degree 2k polynomial because, remember, trace of a matrix is simply the sum of the entries on the diagonals of the matrix. And the entries of a to the 2k are, linear combinations of products of entries of A, taken at most 2k at a time. Okay. So hopefully this is absolutely clear that this, is in fact a degree 2k polynomial in entries of A. And now, I can do the same kind of analysis I was doing in order to, relate the max degree algorithm to the sum of the powers of the degree algorithm. And, here in particular, let's maybe in fact just do it. So if I have G from G and half, then trace of A to the 2k is equal to some lambda I to the 2k, which is at most C root n to the 2k times n. There are n different eigenvalues. The max of them is at most some C root n. So, C root n to the 2k times n is an upper bound on trace of A to the 2k when A is the plus minus 1 adjacency matrix of a graph drawn from G and half distribution. Good. While if G is drawn from the planted distribution, then trace of A to the 2k being again equal to some lambda I to the 2k is at least the largest eigenvalue. And last time we proved that the largest eigenvalue is at least the largest clique, omega. So this is at least omega to the 2k. Okay. So now, if the planted clique omega is bigger than, let's say, 2 times C times root n, where C root n is the maximum eigenvalue, of that we used in the first case, then we again need the same calculation to work out that 2 to the t should dominate n or t should dominate log n. And so this distinguisher actually works. It requires some non-trivial proof, by the way, but this distinguisher actually works at root n, not root log n. And so not root n, root log n. Can again someone tell me why? This is a somewhat of an unfair question because I am asking you for a fact that I probably have not taught you in this class, but just for kicks. Can someone tell me why is actually this distinguisher going to work with work with just omega equals constant times root n and not like I don't need root log n factor here? Why not? So actually, this is a pretty deep fact about concentration of the maximum eigenvalue of random matrices. So we proved the last time that, or at least we gave a very rough proof that n to the point 51 or whatever is an upper bound on the largest eigenvalue of a random matrix whose entries are plus minus one at random. But actually, so first of all, you can prove that the largest eigenvalue is C root n in expectation. And the standard deviation is actually little o of root n. In fact, it happens to be, yeah, let's not even discuss, what the distribution of the eigenvalue looks like. But the largest eigenvalue is a very rigid statistic, Its, its standard deviation is of a much lower order, which means that, because this root log n multiplies the standard deviation, if the standard deviation is of a lower order than root n, that root log n does not matter at all. So anyway, we rely on the rigidity of largest eigenvalue statistic of a random matrix to actually, conclude that this distinguisher, even though, in the previous ones, when we lost root log n's for our high probability bounds, in this distinguisher, we won't lose the root log n's. Okay, good. So I'll just maybe say a comment. We rely on rigidity of lambda max of A for Wigner matrices A to actually conclude that this distinguisher works for omega bigger than some C root n, where C is an absolute constant. And by works, I mean, works with probability 1 minus the law of 1, which is our definition of what it means for a distinguisher to work. Anywho, what have we done so far?
I have this doubt.
Yeah, go on.
So using approximation theory, we can generally approximate high degree polynomials with some lower degree polynomials for univariate things, right? To preserve the value in some fixed interval. Can we do the same thing for multivariate and decrease the degree here?
So let's see, like for example, specifically for this particular polynomial.
Yeah, maybe. Yeah.
So that I think is false. I think there is no constant degree polynomial that can do that can get you a arbitrarily tiny constant approximation of the largest eigenvalue of a matrix. So
are there any extensions like approximation theory for multivariate at all? I only saw for univariate polynomials.
Again, a good question. So let's maybe see if I can recall an example. Okay, there is some. Okay, so let me maybe say it this way. There is some relatively less developed theory of approximation by polynomials in the multivariate setting. You're right, like most of our bounds really come by using the univariate setting and then maybe using it cleverly to get a multivariate approximation out. For example, if you wanted to approximate threshold functions by polynomials or whatever, you basically go and approximate the sine function by a polynomial univariate setting, and then lift it up to work in the multivariate thing. But there is some reasonable theory of approximating by polynomials over product distributions, which really does directly work in multivariate settings. And so the search term maybe for you is noise stability. There is this notion of noise stability of certain functions, and it turns out that it gives you some handle on approximation by polynomials. There's basically noise stability is related to this whole theory, this Fourier analytic theory of polynomial approximations, in some different norms. Usually when you study approximation theory, you study in L infinity norm, like this Chebyshev approximations.
Yeah.
But if you go to L2 over a certain distribution, then there is a lot more you can do using Fourier analytic machinery. Maybe that's one example I can recall off the top that directly functions in multivariate setting.
Okay.
But anyway, like coming back to your question specifically about this, the kind of polynomials we're looking at here, there is no general degree reduction procedure that, can save us over
Yeah.
the degree here. So, essentially what we are doing is tight, maybe up to constants. Good. Okay. So what have we done? We saw, algorithms. The first algorithm was like this edge algorithm, and, that was trivially a linear degree polynomial. The second algorithm was, very easy, but was not a polynomial, but we were able to convert it into a polynomial, maybe, up to this log n loss in the degree. And the third algorithm was somewhat non-trivial. We came up with it the last time, but even that turned out to be a low degree polynomial. So, even if you had your doubts at the beginning that low degree polynomial is a bogus model, what can it really compute? Maybe those doubts are, disappearing just a tiny little bit. It's not such a bogus model after all. It can do something non-trivial, right? That's good. Now, in the interest of time, let's not do the same discussion for the other problem, but let's maybe just note the conclusion of it. We saw, so we could come up with like similar easy distinguishers for the 3 XOR problem. Let's ignore that discussion. We did plenty of that enjoyable discussion right here. But remember the optimal distinguisher that we came up with, or at least what we claimed is optimal to the best of our knowledge, was this lambda max distinguisher for this particular matrix that we built, right? Now we really truly analyze it for 4 XOR, but let's fudge the details a little bit, okay? So last time for 3 XOR, or really for 4 XOR, we saw a lambda max based distinguisher. And if you remember, this A here was an n square by n square matrix built from, the input instance. By the same kind of trick that we did, using trace of a high power, we can again make it a log n degree polynomial and get the same, conclusion out. It can again be approximated and this example is interesting to note because unlike a click where the trivial brute force algorithm runs in time n to the log n, the trivial brute force algorithm for 4 XOR runs in time 2 to the n. There is no n to the log n time trivial algorithm that succeeds here. So even if you were to take this log n degree polynomial and just like spend the trivial amount of time to compute it, which is n to the O of log n, it's actually a pretty non-trivial algorithm because the only algorithm, the only trivial algorithm we know for this problem is just 2 to the O of n time. Okay, but the point is that many of our algorithms, even the ones that compute max or like optimize certain simple functions, can indeed be approximated reasonably well by low degree polynomials. So low degree polynomials are not such a bad model of algorithms, at least in our context. So that's maybe that's all the conclusion of this part. It's very good. Okay, so the conclusion of so far what we discussed was that low degree polynomials are not so bad. Okay, now here is a way in which they are very good. Okay, they're very good or very easy to analyze. Okay, so last time we saw spectral algorithms and we saw that they were somewhat non-trivial to build, right? We could choose a matrix and analyze it and it gives us some result, and then we had to be clever in constructing other matrices which sometimes could improve on the result of the trivial matrix, etc., right? In particular, if I asked you, hey man, give me the best n to the d by n to the d matrix, best in the sense of a spectral distinguisher, there is no easy answer to it. So let me maybe say this: spectral distinguisher, no easy way to find the best. Well, unlike that, the cool thing about low degree polynomials is that you can literally, given a degree bound, I can give you the best distinguisher. So which is kind of cool, right? If you are, into figuring out, what's the best distinguisher for a certain problem, if for whatever reason you knew that low degree polynomials are the best possible algorithms, if you knew that, d equals log n polynomials are the best algorithms ever, then you could literally write down that polynomial and then analyze it to death, right? In particular, you could completely understand, how hard that problem is, at what threshold, things work, at what threshold things break, etc., because of this property. So let me, give you a quick proof of this property, okay? This is the reason why we actually care about them, because, once you are convinced that they are a good model for your problem, figuring out how good they are is actually relatively simple, okay? Simpler than, both sum of squares and also the easier spectral algorithm that we saw last time. Good. So here is a theorem. Let D planted and D null be distributions on 0, 1 to the n. Let's call it, in fact, plus minus 1 to the n. Now, it might appear like this theorem that I'm claiming is like somehow tied down to the hypercube. It is not. But, it's way simpler to carry on the notation, etc. in the settings. So I'm going to restrict to it. You can actually prove, you'll see that the proof is so simple and so general that actually it will extend to any domain, okay? It's just simple, uses the property that there is some distribution and, is doing something very linear algebraic here, okay? So suppose there's a degree D let's see. Then we can explicitly describe the solution to the following problem. It's kind of a weird thing to call a theorem, but okay, let's go with it. Max P is a degree D polynomial. P of G from mu planted, I guess I called it D planted, P of G okay. So first, let's make sure that we understand this theorem. I'm claiming that the best polynomial distinguisher of a given degree is in fact described by this program. Okay, what does this program do? It fixes the expectation of the polynomial on the null distribution. Think of this as normalization. I'm going to hold the performance on the null distribution constant, and then I'm going to find the polynomial of degree D that maximizes the expectation on the planted distribution. Okay? Intuitively, this program is trying to find a polynomial which is as different as possible on the planted distribution from the null distribution. Notice that, the second, like the condition, like this constraint here is really, without loss of generality. Like if there is any polynomial that has different expectations on the two distributions, I can normalize and make the expectation on the null distribution 1. And then, this program is simply trying to find the maximum possible expectation of the polynomial, on the planted distribution. Okay. So let me pause for 30 seconds and make sure that you understand that this program computes the best degree D polynomial distinguisher.
Pravish, do you need the constraint P to have bounded variance?
Let's not worry about that right now. You are right, but it would kind of fall out naturally eventually. Like in some sense, think about, like maybe one way to think about this, it's a degree D polynomial. So there is some natural way that its variance can be bounded, but yeah. Okay, good. So now, let's maybe explicitly characterize the solution to this. Okay. So here's a proof. Now in the proof, So the proof is really simple. Okay, I'm going to do some very, very simple one-line linear algebra. But in order to make sure that the proof is absolutely clear, let's first use the special case when D null is simply the uniform distribution. Suppose okay. Suppose it happens to be the uniform distribution. It can be arbitrary here, right? The theorem doesn't really say what D planted and D null are. But let's say for whatever reason, D null happens to be uniform. This was true if you make n choose 2 in the context of the planted clique, right? G and half distribution, notice that it is really uniform distribution on plus minus 1 to the n choose 2 or 0, 1 to the n choose 2. But you'll soon see that this is not necessary. This is just simple because I've already told you about a good basis for this domain, okay? So then recall the Fourier basis. So if you remember, for all S subset of n, there is this monomial function x sub s, which has the property that D null expectation of xs is 0, the square is 1, and xs xt is 0 if s not equal to t and 1 otherwise. Okay, I hope you remember all these trivial facts. Actually, they are easier to they're also like basically easy to prove visually if you have forgotten some of those. But the cool thing is that that's all. That's basically all I'll need for proving the theorem. So I'll write this p of g. It's a polynomial on plus minus 1 to the n in its Fourier basis. So I can write it like this. Okay, it's a degree d polynomial, so only s of size at most d appear. Okay, so that's good. You all agree that this is how any polynomial of degree d looks like. Now the constraint says that expectation pg on d null is 1. Well, this is if and only if p hat s what did I do? Okay, no, it's fine. I hope it is. Well, this is if and only if the empty coefficient is 1 and everything else is 0. No, actually, well, that's okay. Sorry, I got confused for a second. But expectation of p of g is simply equal to the empty Fourier coefficient of p, which is this is just simply because exs is 0 on d null, and so the constraint simply says that p phi must be 1. In all the excitement of doing linear algebra, I dropped my pen, but I'm back. Good. So this is what the constraint means. And what does the objective look like? Yeah? By linearity of expectation, whatever. And so now, look at this. What is this? This is basically the inner product between the vector of coefficients of P and, this particular set of constants. These are simply constant. These are expectations of the monomials with respect to the planted distribution. Yeah. And so, by linear algebra, so let me remind you, like if you're still confused notationally, then this is the problem. If you just look at the vector of coefficients, I have p phi here, then p singletons, then p doubletons, and so on. I know that this is supposed to be 1, and I'm trying to maximize the inner product of this vector with the vector whose entries are 1, and then at NES, the entry is the expectation of the monomial excess on the planted distribution. Okay. So this is an L2 problem. You're maximizing, expectation, subject to, subject to, the first term being 1. And so, you precisely know, what the solution is going to be. So P has to be proportional to, this vector, right? The solutions to this are, simply, the solutions to this is simply, uh, the solution to this simply, has to be proportional to, the vector of expectations of over the planet distribution. And now I understand what Jeff was saying. I do need a normalization condition, which I didn't include. And Jeff was right, and I was wrong. Which happens a lot. So let me add that normalization condition. Right now, the value of this program is unbounded because, it's not scale invariant. But, this is saying that, the variance of the polynomial over the null distribution is 1. Think of it as a normalization condition. Okay. Good. So now, now you precisely know what the solution has to be. The solution simply has to be, the correct scaling of the vector of, expectations of monomials over the planted distribution. Normalized to have sum of the squares equal to 1. So let's call this P has to be, so P, the vector P has to be, we'll call this, or we'll just say this proportional to mu, D planted. So this particular object here, D less than equal to D at the top of the planted, is simply, my notation for this vector. And, it's nice to think of it this way because, it is simply, one way to understand it is that it's the low degree projection or degree D projection What do I mean by that? Well, if you were to write D planted, so D planted is a distribution, right? So for every point in plus minus 1 to the n, it gives you a probability. So in particular, D planted itself has a Fourier expansion as a function, it's a probability distribution, but it's also, its density function is simply a function on plus minus 1 to the n. So I can write it as D planted hat S XS. And so, you can notice that this particular, so if you remember, okay, let me just maybe do it instead of claiming it. So if you remember, when we first studied some this Fourier basis, we proved that D planted of S in fact can be computed like this. It's D plant expectation over the uniform distribution. D planted of S, X sub S. That's what this coefficient is supposed to look like. And I'm going to simply, open it up. That's what uniform distribution means. D planted X sub S. And now, notice that if I simply absorb this 2 to the n inside, then up to a scaling, this is simply I hope I got that right. It's 1 over 2 to the n times expectation over D planted of X sub S because this sum over here without the 2 to the n is simply, expectation of the monomial X sub S on the planted distribution. Okay. So what, up to a scaling, what we have here is a vector of Fourier coefficients of the distribution's density function, the planted distribution's density function, truncated to degree at most small d. So that's the reason for this notation over here. Okay. And so you see in particular that we were able to completely characterize the optimal solution to this optimization program. Namely, it has to be the truncation to degree d of the density function of the planted distribution. Okay. Now we use the fact here that, d null was uniform, but actually, the same proof works for any distribution where instead of, the monomial basis, use the right orthogonal polynomial basis. So the nice thing about monomial basis was simply that, it's a graded basis for functions on plus minus 1 to the n, which has, this orthogonality properties with respect to d null, the uniform distribution on the hypercube. But actually you can build such a basis for every distribution. And, one way to do it is simply do Gram-Schmidt, start by, taking the degree 1 monomials and, run Gram-Schmidt on them. Then, just continue to do it sequentially. The only thing you need to ensure that this degree property holds is that, you handle degree 1 before degree 2 before degree 3, and so on. If this comment did not make sense, doesn't matter. Take my word for it that you can literally do the same process with just a different basis, which is appropriately chosen for the d null at hand. Okay, and then the same proof basically works out. And the reason it does is simply because, what you're doing is simply an L2 proof, right? Like you're simply doing some basic linear algebra here. So it's not a big surprise that it's going to work out, but each time the solution would be truncated relative planted density. Okay, so this is the word I'm using for d planted restricted to less than or equal to d. Okay, it's basically, it's good to understand it as a truncation of to low degree, of the density function of the planted distribution. Okay. Well, very good. So one thing we can conclude right here is well, I guess I did not write my comment. Okay, so here is something to remember or conclude. So remember the optimism. So okay, maybe we write the conclusion and discuss then, I guess. So conclusion, degree d polynomials distinguish between d planted and d null if and only if the value, well, I guess we had a solution, if and only if d planted less than or equal to d, this actually equals sum over s bigger than or equal to 1 d expectation excess d planted square is bigger than 1. So, the 1 here is the expectation of this, so, in particular, what I did was I used the solution we computed for the optimization program we set up. I gave you the optimal degree d polynomial. And then using it to write the objective value of the optimization program we set up. And I'm saying that, the optimization program's value must be bigger than 1 because 1 is the value for, 1 is the expectation of the polynomial for the null distribution. Okay, well, actually 1 is also the expectation, and we have normalized so that the variance of the polynomial on on the null distribution is also 1. So what we are saying is that if the expectation of this polynomial on the planted, so this quantity is expectation of the polynomial on the planted distribution. And we are saying that if this is bigger than the expectation on the null distribution, plus some big, think of some big number b times the variance on the null distribution, the same kind of calculation that we were doing for the specific distinguishers earlier, then in fact this distinguisher will succeed. And we set up the program so that both the expectation of the polynomial is 1, and by appropriate scaling, the variance of this polynomial is also set to 1. And so if I now choose the polynomial to have if I can somehow find a polynomial of degree d which has, after this normalization, expectation over the planted distribution much bigger than 1, then I in fact have a distinguisher which is exactly this condition here. Okay. And so the cool part about all of this simple analysis is that we have a concrete degree d polynomial in our hands. We can just go and test it. Okay. Good. Well, given that low degree polynomials are so easy to analyze, it would be great if they turn out to be, in some sense, optimal algorithms. Okay. And so just like last time, we saw some connections between sum of squares and spectral algorithms, you might ask, is there a connection and the answer is yes, okay, in some tenuous, simple sense, which I will describe. Let's see. Actually, let me describe the connection, then we'll take a break, okay? So that's the right answer. Yes, probably. Okay. And the yes part is, well, I'll explain both parts to you right now, but the probably part relates to a conjecture that we do not know how to solve. I'll describe the conjecture to you, once I describe this connection to you. So, so somehow, the upshot of what we did so far is that all the algorithms that we saw, at least in the previous class, were captured reasonably well by this low degree polynomial method, at least if we allow log n degree algorithms or log n degree polynomials. Then we saw that they're also very easy to analyze the performance of. In particular, we can completely describe what polynomial is the best one to use given a degree bound. And now, we want to somehow show that, in some cases, this is all there is to analyzing even sum of squares, which seems like a much more powerful and non-trivial algorithm. Okay. So let's maybe describe. Okay, let me tell you what this connection is. Okay. And so, this goes, for whatever reason, this connection goes by the name of pseudo calibration. And actually, what I told you is completely the reverse historical order of how all of these ideas were generated. There was no low degree polynomial method that arose first. What happened was, people were trying to prove sum of squares lower bound. So let me maybe make a historical note, given that we are discussing this. So people were trying to prove, lower bounds for some problems in, for the sum of squares algorithm, for high degree sum of squares algorithm in particular. And, for some problems, they succeeded. So in particular, Grigoriev succeeded in proving lower bounds for, 3 XOR. And later on, people were able to generalize it to some other CSPs, including 3SAT, etc., via reductions, some of which you probably have already seen now on the homework and probably done it and finished. Well, you still have a few days if you haven't finished yet. So yeah, so good. But for some problems we succeeded, but for others we actually were stuck, and it felt like we were stuck badly. And the examples of such problems included, the click problem. So exactly the one that we discussed earlier today. Click on G and half. But there were, several other problems. Some of them motivated from machine learning, somewhat machine learning-ish motivations. And so, if you heard of this problem of sparse PCA, it was, somewhat similar. There's also this other problem of tensor PCA, whatever, doesn't matter what it is for us. But there were, basically a bunch of problems that some people wanted to prove lower bounds on, but were unable to, maybe for a few years. And one of the issues was that um, natural. So if you've seen so far, the way we prove lower bounds is by constructing a certain pseudo distribution that seems to satisfy the constraints. Of course, we have to go ahead and argue that it succeeds in satisfying all the constraints of being a pseudo distribution. But the way to prove lower bounds is to set up some refutation problem, and then find a pseudo distribution which is consistent with the constraints, right? This is how we prove lower bound. This is how we prove lower bound for random 3 XOR, etc. Okay. So it turns out that in these problems, and in several others, natural, whatever that means, natural constructions of pseudo distributions are bad. And actually, believe it or not, at some point it was such a craze that people wrote papers about showing that the main result of these papers was simply proving that a certain natural construction does not prove a SOS lower bound. So we were coming full circle here. And I'm calling it some people, but those people included me. So some of these things that I'm laughing at now actually were done by me. Anyway, so that's what happened. Very good. And then eventually, to prove the right lower bounds for all these problems, actually this problem first, people invented this idea of pseudo calibration, which was basically a way to relate distinguishing problems and the failure of the low degree polynomial method to constructing SOS lower bounds. Okay. And well, actually, it's not a full equivalence. It does not somehow tell you that if low degree polynomials fail to distinguish between d planted and d null, then there is a lower bound for d null or whatever. But it at least gives you a construction of a pseudo distribution, which you to then analyze. So far, the analysis itself is not mechanical, but at least it resolved this issue that it gave some constructions of pseudo distributions to work with. And eventually, people were able to analyze it for the click problem, and then eventually for sparse PCA, for tensor PCA, and get the right lower bounds for all these problems using this machinery. So that's basically the history of how this came up. And then what happened was that in the aftermath of these papers, people basically began to analyze this low degree method as an interesting class of algorithms by itself. And so now there are like I don't know, at least 50, probably 100 papers. Well, 100 is probably too much. At least 50, maybe at least 20 to 50 papers that simply are proving lower bounds on the low degree polynomial method for certain classes of interesting problems. These are a lot harder problems to prove SOS lower bound, etc. for. So these lower bounds are taken as evidence of computational hardness, etc. But anyway, so the history is kind of reversed. The low degree method kind of arose naturally in the context of proving SOS lower bounds, but now it has like a life of its own. Good. So after the break, what I'll tell you is the following, and it's not really a theorem. So let me just maybe make it a statement. Suppose there exists a deplanted such that degree d log n polynomials fail to distinguish between deplanted and some distribution d null. Then there is a candidate pseudo distribution of degree d that's consistent So, the way to interpret this statement is to think that, if you wanted to prove a lower bound for the refutation problem on some distribution D null, then one way to go about finding a candidate pseudo distribution is to forget about pseudo distributions and find instead some planted distribution which is indistinguishable via large enough degree polynomials from D null. And then, once you found such a distribution, you can actually use it to mechanically give a construction of a pseudo distribution, which is probably okay. I don't know. It's a construction. You will still have to work hard to analyze it after. Okay. Good. So, what we'll do after the break is, quickly sketch how this procedure looks for 3XOR. And then, I'll state the pseudo calibration conjecture. This conjecture simply says that, for a reasonable class of problems, it's the same class of problems that we did not define the last time in the context of spectral algorithms, that whenever low degree method fails to distinguish, then in fact, there must be a sum of squares lower bound for the associated refutation problem. Okay. In fact, let me just say just that, because the concrete details are maybe not completely relevant for us. So for a large class of average case problems, if, so these are described by, distributions D null, if there's a deplanted such that deplanted is indistinguishable from D null for, let's say, D log n polynomials, degree polynomials, then okay. We don't quite know how to prove this conjecture yet. You saw the last time that, we were able to relate the existence of a SOS lower bound for refutation problems to, success of spectral algorithms. But, we haven't been able to somehow replace spectral algorithms by low degree polynomial indistinguishability or whatever that we need right now. It would be especially nice in the context of analyzing such algorithms because it's so easy to analyze low degree polynomials, as you saw today. And that's basically the motivation behind this conjecture. This was made in a 2017 paper. We don't know a proof of this so far. But, if this conjecture is true, then in fact, it would indeed be true that for at least some reasonable class of problems that includes, both the examples that we saw earlier and many more, low degree polynomial indistinguishability would in fact, be enough to imply a sum of squares lower bound for the associated refutation problem. Anyway, so, when we come back from the break, I'll tell you a little bit about, how this method works for 3XOR. And we'll try to end early and, at least I'll try to end early and, see if we can spend a longer time on questions. All right, so let's meet back at 5:51. Very good. So let's describe pseudo calibration, okay? And because we are not proving, well, in some sense, we are not, well, there is a mathematical theorem in there if you really squint hard enough, but there is no strikingly new theorem that I'm going to tell you. And so, we'll keep it brief because it's it's simply a discussion of this technique to construct a pseudo distribution. And so in order to describe this technique, I'll just do it for a special case of 3XOR, where we already know of a lower bound. Where we not only already know of a lower bound, in fact, we proved it in the class in, relatively gory details. And so today, we will construct a pseudo distribution which satisfies, all the 3XOR constraints when m is like, n over epsilon square, whatever. But we will not use all these tricks that we had to when we did it the last time. So if you remember, the 3XOR system looks like BI XCI is 1, for all 1 less I less m, xi square is 1 for all 1 less I less n. Let's call this system
I
A.
can't see your screen.
Ah, yes, yes, you
You
can.
guys will just like waiting to see how long it takes for me to notice.
Well, because it shows me that I'm sharing screen from this side, so it's yeah, it will take me infinite time to notice.
No, everyone else in the class.
Oh, they're probably on Scribble in their
That's where I
defense.
was. So that's where I'm gonna say I was.
Okay. Yeah, okay. So let's say m is, at least Cn over epsilon square. And, so like this is large enough so that, no x satisfies in the null distribution, no x satisfies more than half plus epsilon fraction of the constraints. And remember, today we fixed C1 through Cm. So the hypergraph was fixed. So only the BIs are, um, um, the average case data, like only the BIs have a distribution associated with them. And so if BIs are chosen uniformly random bits independently for each 1 through m, then, again, as we said earlier, by Chernoff plus union bound, no assignment satisfies more than half plus epsilon fraction of the constraints. And you could ask if sum of squares, can distinguish, or sum of squares can, refute the system, because there is clearly no solution to the system. And in class, in earlier lecture, we proved that omega n degree SOS cannot refute A so long as the hypergraph H has this property of expansion. So if you've forgotten, let me remind you what this expansion was. Expansion simply means that for all subsets T of M, so these are, think of them as subsets of clauses, if you will. Actually, here's a diagram to help you. It's the same diagram we drew during, proving the XOR lower bound. So, each CI has like 3 variables in it. So those are the edges. And for each CI, we have a plus minus 1 bit associated with it. And so, if I look at any T, a subset of clauses or equivalently subset of BIs, then I'm going to say that the hypergraph is expanding, and I'm not even going to go into the parameters today. I'm simply going to describe it as T is, for all sets T of at most, let's say, n over 10,000 constraints, the union of constraints CI, has at least 1.7 times T variables. So, here I'm looking at CIs as subsets of variables. Remember, each CI has 3 variables. So the maximum number of variables that you can have in this union is 3 times T. But of course, they can be repeated things, right? Like different clauses can contain the same variables. What we are saying is that, you can't find a large set of variables, large set of constraints that somehow are, very, are sharing too many variables. Okay, so in some sense, any large set of constraints must contain 1.7 times the number of constraints, 1.7 on an average per constraint, unique variables, if you think about it. Okay. So this, if you remember, this was the notion of expansion we used to construct the lower bound, both construct and analyze it. We'll also assume it right now to describe how pseudo calibration works. Actually, the way pseudo calibration works would not depend on this expansion, but in order to make the construction meaningful, we would require this. So we'll see, how that works in a second. Okay, very good. All right. So what's the idea of pseudo calibration? So pseudo calibration, is a way to somehow use an auxiliary planted distribution to come up with a pseudo distribution satisfying A. Okay. So how's it going to do it? Well, Here's the idea. So actually, I'll say it in words first and then describe what it means. The idea is to set the pseudo distributions, let's say expectations of any monomials, to be low degree truncations of the planted distribution. So just like, remember, the best polynomial happened to be this degree small d truncation of, the planted density. We will somehow, choose this equidal excess for every s of at most d to also be low degree truncations of the planted density. Okay, so let me describe to you what that means. If I were to compute, so let's maybe think about the planted density now, right? Suppose, so okay, so E twiddle mu xs for all s at most d, so fix an s, okay, or actually fix s subset n, let's say, s is of size at most d, where d is the degree of the lower bound you're shooting for, then, you need to describe to me what this value would be, right? So if you remember, when we constructed when we proved Gregoriev's theorem and constructed the pseudo distribution, we used this, this idea of derivations, etc., to come up with excess, right? But let's imagine that, Grigoriev wasn't here to help us. Instead, all we have is a planted distribution, the same planted distribution that we saw at the beginning of the class. Okay, we're going to somehow let it help us in inventing the right value for, pseudo expectations of excess for every s. Okay, that's basically the idea of pseudo calibration. So the observation is that whatever this is has to be a function of the data, like function of, the input instance, which is completely described by this vector b bar. And remember, b bar was supposed to be, a vector in plus minus 1 to the m, right? Still with me? Now, any such function, because, so pseudo expectation excess is like some nice function, we care about it, but it is still a function in b bar. B bar is a vector of bits in plus 1 minus 1 to the m. So every function like this can be written as, so actually let's call it f hat s b bar s. Oh no, let's maybe use t. Since right? Any function on m-dimensional hypercube, including this function, can be expanded as a polynomial. And remember, b bar t is simply the monomial. Okay, and remember, bi is on the right-hand sides, okay? And those are the only inputs to, those are the only things that vary in instances because the hypergraph H itself is fixed. Okay. Now, if I were to compute this quantity, so if instead of computing this quantity for, the pseudo distribution, which I don't know of, if I were to compute this on, deplanted, what would it be? What would f hat t be? So let's, the coefficient of this at some t would simply be the expectation over deplanted of xs. So remember, deplanted chooses both x star and the b stars at random, and there is some correlation between x star and b star. Remember, b star i's were chosen to be equal to x star ci's. And so if I were to compute this quantity on the planted distribution, I would get this expression. And this in particular is a number, right? Like this, the right-hand side is a fixed number. So let's maybe, yeah, okay, good. So let me just say that that's what. Okay. So if you were to compute the expectation of x sub s, the monomial x sub s, which is basically the product of xi's, where x is the assignment that satisfies the instance. If I were to compute this quantity on the planted distribution, literally, which means that if I wanted to write as a function of b, the input b, I would simply write this as sum over t. This is really the Fourier coefficient over there. So let me write it like b planted x s star b star t. Only the notation is somehow confusing here, but all I did was, I forgot for a second that I'm trying to define this quantity on, I'm trying to construct some pseudo distribution. Instead, I simply started writing down how does the planted density look? How does the planted distribution look? Said, hey, you know what? I'm going to compute. So this planted distribution, under the planted distribution, there is a certain expectation of x sub s for every possible s. And and this particular expectation has to depend on the right hand side b's that I see, in my instance. Because it's a function of b, I can expand it as a polynomial, as a Fourier polynomial, and then I can compute the coefficients by this Fourier inversion formula that we saw earlier. And so what I did was just apply that to write the planted distributions expectation of any monomial x sub s as a function of the bit the right hand side vector b as this polynomial in b. Okay, and so here is the idea. Yeah.
Oh, the left-hand side should be pseudo expectation, right?
There is no pseudo expectation right now. I'm simply writing down the function which gives me the value of expectation of monomial x sub s on the planted distribution.
Okay.
Okay, let's make sure that we understand this notation. If look at the look at the 3 XOR instance, let's say I, generated from the planted distribution. Remember how it was generated? It you first chose a x star at random from plus minus 1 to the n, right? Then you chose bi star as simply the values that this gives to each of the equations, right? Each of the triples that appear in your instance. Yeah. So now imagine that somebody did not tell you the x star. All you got to see was the instance generated by the planted distribution. So what would you get to see? You will get to see C1 up to Cm, which is fixed, and you'll get to see B star 1 up to B star M. Okay. Now, of course, the person who generated the instance for you would not be so benevolent to tell you that these are stars, as in they will not inform you that there is some x star behind it or whatever. So you'll just see this B1 through Bm. They just happen to be equal to B stars computed for some unknown but randomly chosen x star. Yeah. So now for every B's, for every every choice of instance from the planted distribution, I have under the planted distribution some expectation for each monomial, right? So if I compute for an instant, so let me see this. Okay, for a fixed instance, xs is actually equal to x star s, as in the assignment that satisfies. If I wanted a distribution, the satisfying assignments for the instance were produced, then there's a unique satisfying assignments. And so the monomial xs computed at that satisfying assignment would simply be equal to x star s, which is simply equal to the product of the bits in s of x star. Yeah. Now I want to average this x star over the planted distribution. Okay. Or for a fixed b. Okay, so let's maybe. So I'm not sure if my explanation is confusing, more confusing than what I said earlier, but let's maybe say this. So D planted condition on B okay, because if I fix B, if I fix the right hand sides, then there's a, like, this is just a statement that, there's a unique assignment or whatever. Okay. So now what I'm trying to understand is, so, this particular thing is different for every B, right? If I only tell you the right hand side, the quantity that will turn out in this expression would be different. If I were to write it as a function of B, it's going to be a polynomial in B. Yeah. What I wrote down here is simply that polynomial. And then I computed what its coefficient should be by just averaging. Okay, so in other words, the the coefficient here is simply the correlation between B star T, the monomial, and XS star, over all instances drawn from the planted distribution. Does it make sense? All I did was like write this function as a polynomial in B. Okay. And now, what I'm going to do is, something weird and silly, but, sensible in retrospect. I'm going to set pseudo expectation. Now, I'm trying to define this quantity. I don't know what it is. It also is supposed to be a function of B. Okay. And I'm going to set it to be the truncation of this expression that I wrote down for the planted distribution. Just like, the best polynomial happened to be a low degree truncation of the density function of the planted distribution. That's exactly what I'm going to do here. Okay. And this is a definition. There is no, in some sense, there is no independent, there is no different definition of mu here. This is a pseudo distribution I'm defining. And I'm just setting it to be the low degree truncation of the same expression when it is computed on the planted distribution. Okay. So in some sense, you can think of this as, you can think of this as saying that, mu pretends, so mu is a pseudo distribution, but it pretends as if the instance was chosen according to the planted distribution. And this pretense is actually good only for low degree polynomials. So in particular, like one consequence of this for all polynomials f, okay, and these are, let's say, polynomials in both x and the instance I. So remember, for us, instance is completely described by this vector b. For all fxb polynomials such that degree in x is at most, let's say, d, degree in b bar is at most, let's say, tau, it holds that the pseudo expectation of fxb bar equals so if I average the pseudo expectation fx b bar, so fx b bar, is a function of, the pseudo distribution mu that I defined is a function of b. For each b, there is a different pseudo distribution. So if I compute the pseudo expectation of fx b bar and then average it over all possible values of b bar when chosen according to the d null distribution, then the expression I computed ensures that this is equal to the average over both x and b bar, which are jointly and correlatedly chosen in a deplanted distribution for the same polynomial. So as long as f is a low degree polynomial in both x and b bar variables, the expectations with respect to deplanted match the pseudo expectations on an average over the null distribution. Okay. Well, okay, that's what it is. And instead of going into detail, let me maybe assert the following now. Here's, an observation. Or actually, let's do it. We have some time. So let's analyze this expression. So let's maybe analyze this expression that we wrote down earlier. So, for xs, we wrote down the expression as sum over t. Let's try to understand what this expression is. So over the planted distribution, if you remember, b star t is actually chosen as a fixed function of x star, okay? So remember that bi was supposed to be x star ci. So this is equal to expectation deplanted xs star Now I'm just going to recall that bi star equals the product of bits in x star for ci. Yeah. And now, let's understand what this expectation is supposed to look like. Notice that I only have a function of x star in this expectation. The distribution of x star in planted distribution was uniform because the assignment x star was chosen at uniformly at random from +1 -1 to the n. Yeah. So when is this, when is this expression non-zero? So this is non-zero if and only if every variable appears with an even power. You have a product of x star ci's, which equals the product of variables appearing in constraint number I. So many variables appear multiple times. So each variable would have a certain power sitting on top of it. If it happens to be odd, then, because each bit of x star is independent and has zero expectation, all odd powers, any odd power will lead to a zero expectation. So, this expression is non-zero only if the power of every variable happens to be even, which is same as saying that the number of the variables okay. So this expression is non-zero only when, if you look at, the multi-set of CIs, when you union over this, this index set T, then the variables that are, appearing odd number of times exactly equals to the set S. That's the only way that this expression can be, non-zero. Actually, this characterization appeared before, even though this time we didn't force it. If you go back and look at your notes about the Gregorian lower bound, this is same as saying, this is equivalent to saying that C1 CI, or actually, let's maybe say this is equivalent to saying that the symmetric difference of CIs in the set T exactly equals the set of variables S, or the set CI So, like if you remember the way we constructed Grigoriev lower bound, we, had lots of constraints, and then, we derived new constraints from them by multiplying, various sets of subsets of constraints. What we have learned is that the coefficient at T of, the pseudo expectation of XS, which is equal to this value here, is non-zero only when the subset of constraints in T derive S. Okay. And so actually, you can use this reasoning to prove. So here is a claim that I actually won't prove. If tau is, less than n over, let's say 10 to the 4, because the point of this claim is that if you choose the threshold to not be too large, then the definition that we came up with is actually exactly equal to, the construction that we used to prove Grigoriev's theorem. Yeah, I guess that's the point I wanted to make. That basically this pseudo calibration idea is a way to use a planted distribution which is low degree indistinguishable to define a candidate pseudo distribution. A candidate pseudo distribution. We expect that this pseudo distribution would be reasonable only when the planted distribution is low degree indistinguishable. For this, we only have examples, as in we can prove that this property is true, for 3XOR and for CSPs and for planted clique and for sparse PCA and tensor PCA. But the general result that asserts this is the pseudo calibration conjecture I said earlier, and we don't know a proof of that. So, the fact that this construction is any good and that its any goodness relates to the low degree indistinguishability that, low degree polynomial indistinguishability that we defined earlier is basically conjectural. Okay. But that's basically it. I guess, this exercise, which, you should probably try to do it in more detail, is to just convince yourself that, this kind of a weird definition, using a planted distribution of a pseudo distribution for 3XOR happens to be the same as the construction that we did in the context of Grigoriev's theorem. So, one could think of it as, some evidence that, there is some reasonable thing that pseudo calibration does, at least, for the 3XOR problem. Of course, as you see, it doesn't really help you prove that it satisfies all the properties of a pseudo distribution. In particular, it does not help you prove positivity or PSDness. You still have to go ahead and, do it perhaps using the same kind of ideas that we did, in the proof of Grigoriev's theorem. So there is no mathematical theorem that it helps you prove in the context of SOS lower bounds. It just gives you a good candidate pseudo distribution, which under the pseudo calibration conjecture, would in fact be a valid pseudo distribution, but we don't know that. Anywho, that's basically all I wanted to say. That the low degree polynomial model is simple at first, but actually quite powerful. And that it's very easy to understand in that we can actually characterize the best distinguisher and then in fact, usually relatively easily compute its performance. And the nice thing is that it seems to relate to the performance of sum of squares for the related refutation problem, modulo conjectures and guesses. So this is, rather imprecise and vague, but that's what we know so far. And so, if all of this is reasonable, then you might be inclined to use lower bounds on low degree polynomial algorithms for distinguishing problems as some evidence of average case hardness, which is what, several recent papers actually do. Well, that's it. That's all, for today's lecture, and also the very last lecture. So we can now, take a long pause and take any questions. And, as I wrote on the Diderot post, it doesn't have to be about this particular lecture. Today we can spend, the remaining time discussing any questions that you might have related to the class, of course. Yeah, I'll write the summary. All right.
Ish.
Yes.
I think you need to explain the the pseudo expectation hats, because I noticed you didn't ever write you didn't ever use the pseudo expectation with the hat on it in this lecture.
Yeah, good.
You need to explain this.
I thought it was okay. It was a funny but bad notation, but let's do it. So, so I have tried to do this pseudo calibration business in other talks before, and in those talks I used to use this funny notation. I used to think of the pseudo expectation of x sub s as a function of b, right, in the context of 3 XOR, and then Fourier expand it. And for any function, if you Fourier expand it, we usually write the Fourier coefficients with a hat on top of the function you have. So, if you were to do it for the pseudo expectation of this monomial x sub s, you might be tempted to write it as and you might also be tempted to read this as a pseudo expectation hat. And if you are someone like Peter or me who finds this funny, then you might actually be overjoyed here that you have a weird object which you call a pseudo expectation hat. You might actually want to make an actual hat out of it, which is what we are doing. Yeah, so I'll let you know when they arrive, but for all of you who have carried on strong so far in the class, I have a return gift, which is a hat with a pseudo expectation written on it, which you could read as pseudo expectation hat. All right, so yeah, one question answered. What else can I answer?
I'm kind of just like broadly curious, like what it's not really about this lecture, but like what do you see as the sort of like hot things in SOS right now, and what are the directions that you're most excited about going forward? Not necessarily in your own research, but just like the subfield of SOS.
Sure. yeah, I think, in some sense, even though maybe we didn't explicitly do it many times, but a lot of the open problems are kind of hidden in many of our lectures. Of course, we didn't cover a lot of material, so there are a lot of open problems hidden in parts that we didn't cover. But for example, if you were interested in average case complexity, then I would say, um, understanding the pseudo calibration conjecture is, I would say, a very nice open problem. um, you know so it's probably not super easy, given that uh, you know people have spent maybe 3-4 years thinking about it, but it also can't be that hard, right? Like, it's not a conjecture that has been open for a long time. And so yeah, I think, and this would be really cool, because think of it as a method to completely mechanize proving SOS lower bounds, because low degree indistinguishability is so easy to prove, and so relatively easy to understand, that if there was a proof of this conjecture, you'd basically be simplifying a whole lot of hard jobs. And to be honest, for a long time, in several in the times that I've thought about it, for several times I actually thought that I had a proof of the conjecture. It just happened to have bugs, but you might take that as an encouraging sign that maybe a proof is not supposed to be that hard. But yeah, again, that I think is a nice open problem. Also, in some sense, it beyond just mechanizing SOS lower bounds, which you may or may not like, I think it tells you something nice, right? Like, it somehow formally connects the different kinds of average case problems which we saw. In particular, the conjecture relates the refutation problem's complexity to the complexity of distinguishing planted from null distributions via low degree polynomials. So it's not just, it's not just about sum of squares versus low degree polynomials. It's also relating, in some sense, the complexity of two interesting types of average case problems: the distinguishing problem and the refutation problem. And so yeah, there's maybe multiple reasons to like this conjecture. And this conjecture actually falls in this maybe a relatively broad line of work, which tries to relate various models for understanding average case problems. So maybe one implicit reason, I wonder if I mentioned it in one of the previous lectures, but one of the reasons we are doing all of this is because it's not so easy to understand the complexity of average case problems in the way that we are able to do it for worst case problems. For example, if I ask you, hey, how hard is worst case 3 XOR, right? Then we kind of have relatively well-defined methods to approach this problem. In fact, for this problem, we completely understand how hard it is, right? The way we do it is, if we wanted to prove hardness of the satisfiability versions, then we prove NP hardness, and we kind of have a well-developed machinery of reductions for that. If you wanted to prove hardness of approximation, we have a pretty well-developed machinery of PCP theory to do that, and in fact, that's how this theorem is proven. And so, in some sense, we have a pretty good theory of hardness of approximation for worst case optimization problems, right? Modulo P versus NP. We do not have such a neat theory for average case problems, right? Even if you were willing to make new assumptions, let's say that you are okay with making additional some average case P versus NP assumption. Let's say, for example, random 3-sat is hard. We still do not know how to build average case complexity on some one single assumption like this, because the reductions that we do in worst case complexity usually modify distributions, which means that they don't really work to prove hardness of natural distributions that arise in average case complexity. And so in the absence of such generic methods that one could use to ascertain easiness and hardness of problems, what people do is like come up with various restricted models. Like if you're a learning theorist, you might like the so-called SQ model, which is what their go-to model is for proving lower bounds on problems. If you are a statistical physicist, you might like belief propagation or local algorithms. It's some other models we did not touch upon, but are kind of related to this low degree polynomial, if you will. If you are, let's say, for lack of a better word, complexity theorist, you might like, SOS semi-definite programs, and so on, right? Like you might like many different models which are motivated from applications in, one or more areas. And so one broad project that I think people are interested in is, can we somehow combine all these things under one umbrella? Can we somehow unify these several ways of investigating average case problems, which are more field specific? And so, for example, there is a very recent paper that proves that under some conditions on the average case model, this so-called statistical query model is actually equivalent to low-degree polynomial model. It's a very recent, like a maybe 3-4 months old paper. And the pseudo calibration conjecture is another example of a somewhat similar motivation. But largely this area remains kind of not well understood. In particular, there is maybe very few rigorous connections between the failure/success of algorithms like belief propagation or other local algorithms that physicists like to use, and sum of squares, for example. And there are problems for which both are interesting. And again, one example problem that we didn't do in the class is this problem of community detection. And for special cases like this, people have managed to somehow relate sum of squares and the low degree method to the predictions or these algorithms that physicists like to use. But again, at a more general level, we do not know of such connections. So I think there is a whole area here which is trying to do these kind of things. And that's maybe the broad maybe a couple broad directions in average case complexity. In worst case, a lot is basically unknown, and in some sense maybe not much has happened in the past few years, to be honest about it. For example, we don't even know if degree 4 SOS can beat the algorithms that we saw for max cut or more generally unigames problem. It's like such a simple question, such a simple concretely stated question. Degree 2 SOS gets you this alpha Gomez-Williamson approximation. Degree 4 SOS, we don't know. Can it improve on it? We don't know. If it does, then it will just prove the unique games conjecture. But we haven't been able to prove that it doesn't. Similarly, such questions exist about several problems, not just max cut or unique games, but this question that maybe we only lightly touched upon is the related problem of small set expansion, which is related to unique games conjecture. Again, we do not understand, how good or bad is sum of squares for small set expansion problem. And there are like concrete open questions for problems that we, saw in the class. For example, we saw this problem of computing expansion of a graph, or what is also called as sparse cut problem. And if you remember, we saw this ARV theorem that proves order root log n approximation using degree 4 SOS, right? Long ago in the 3rd or 4th lecture of this class. And basically nothing is known beyond what we saw. We don't even know if you can improve degree 4 SOS itself. We don't even know if what we did is right analysis for rounding degree 4 SOS. Higher degrees, nothing is known. And for all, like as far as we know, there could be a constant approximation algorithm using degree 6 SOS, for example. And we do not know that. Yeah, so like in worst case complexity, I think there are basically several basic problems, including essentially everyone that we studied in the early parts of this class, where performance of even basic like constant degree SOS, like degree 4 or degree 6 SOS is unknown, and those are all widely open. One concrete question, by the way, that I like in this direction is probably something I mentioned in the class on max cut, which is there a 2 to the O of root n algorithm? Actually, it doesn't need to be root n. I mean, just guess my go-to sub-exponential function. So instead of like using degree 4 or degree 6 or whatever, can you use sub-exponential time to beat the guarantees of Gomez-Williamson algorithm that we saw in the class for max cut problem? Now unlike degree 4 or degree 6, if this question has a yes answer, it does not say anything about unique games conjecture. Like this question could have either yes or no answer. It does not refute or prove discrete unique games conjecture. There's no relationship whatsoever. And so that's the reason, one could think that this is an easier question. And we do not know what the answer to it is, but it's kind of a natural question, right? Like maybe one reason to be interested in this question is that we mentioned but did not do this algorithm in the class, but there is this global correlation rounding based algorithm for unique games. Right, there is a sub-exponential time algorithm using n to the epsilon degree SOS for solving the unique games problem. And so this question here, despite not saying much about unique games, really does try to, whoa, I wonder if iPad pens run out of ink because my pen has stopped writing. Let's see. Oh, okay, there it is. Apparently our whiteboard is huge. Anyway, so there is a 2 to the n to the epsilon algorithm for solving unique games. And so, in some sense, this question is trying to ask, is UG strictly harder, strictly easier than maxcut? Right, because, maxcut, if you remember, is a special case of the unique games problem on binary alphabet. And we do know that maxcut is at least as hard as UG because we can reduce the unique games problem to maxcut. Like this is the reduction in particular that says that, if unique games conjecture is true, then you cannot beat Gomans-Williamson algorithm's guarantee in polynomial time, right? So we know that maxcut is at least as hard as unique games, but we do not know if maxcut is strictly harder. So if there is a sub-exponential algorithm, in some moral sense, you could say that, well, okay, maybe it is not strictly harder. But if, for example, there is no such algorithm, then it seems legitimate to interpret that as saying that maxcut, at least in this sense of sub-exponential algorithms, is strictly harder than the unique games problem. Anyway, so yeah, so that's maybe my motivation for asking this question. And yeah, we don't know we don't know an answer for this concrete question either. Yeah, I know. I don't know. Yeah, that's maybe a small list of nice open questions. Does that help?
Yeah, definitely.
So actually, such a seminar has been taught like a few times. So when I was a graduate student, I attended a seminar that Boaz Barak taught in 2014 on sum of squares, but the topics were very different because most of what we did actually wasn't known in 2014. And at that time, Boaz posted a list of open problems. I think it is on his blog. I think it's on Windows on Theory. I feel like maybe only 2 or 3 out of that list of, pretty large list of problems has actually been solved after that. What has happened instead is that, instead of solving open problems, these pesky people, just found new problems to solve instead. And so that also is a good message in some sense, right? Like sometimes maybe the best thing you can do is not go and pick a list of open problems and solve them, but maybe you can actually chart out new directions yourself, right? Like it's a pretty powerful technique. It's largely in the beginning stages, I would say, of its usage. It's only in the last 5 to 6 years that we've been able to get proficient in using it and wielding it on problems. And so, who knows, in 2-3 years, what area of problems that you would be able to solve. Like, in 2013 or something, it was completely unclear whether you could solve problems in machine learning or average case complexity using sum of squares. And then it took like a couple papers to completely, shift gears. And that's why, these problems never appeared on people's radar. Like, in 2014, Boaz Barak did not ask, learn mixtures of Gaussians using sum of squares because, it was off radar for people. And so, yeah, maybe the best open directions are the ones that are not on this whiteboard and probably on no one's whiteboard. More questions? We have more time to kill.
Can you briefly explain some attempts to prove the pseudo calibration conjecture?
Ah, it's a good
Or
question.
how hard it is to prove?
Yeah, it's a good question. Yeah. So actually, it's also a point that I forgot to make. So that's a good question. So, last time we saw, I gave you this vague statement. And yeah, actually both, I'm guilty of giving you only vague statements, this and the last class. But yeah, that's what we can manage in the time we have. So, but the statement I gave you the last time was that, if SOS can distinguish really by solving the refutation problem, then let's say, in fact, we said degree D SOS, then we said there exists, an n to the D by n to the O of D by n to the O of D matrix with entries that are degree D polynomials such that lambda max of A is a distinguisher, right? This is the statement we wrote down the last time, where we were trying to say that spectral algorithms are as powerful as sum of squares for a large class of average case problems. So for that we did not define. So now actually this should make you feel a bit queasy already. Today we took lambda max type algorithms and were able to simulate it using up to some log n factor loss. We were able to simulate it using polynomials, right? So a natural approach is to take this matrix and approximate lambda max by trace of some log n or whatever d log nth power of A, which is a low degree polynomial, right? So we could try to apply the LP L infinity trick today, right? And the quick bait and switch that I did on you earlier is actually the reason why this doesn't work, and it's also the approach that I think at least I and a bunch of other people spend quite a bit of time on. So the argument that we use today, doesn't work for lambda max. It actually works for algorithms that use absolute value of lambda max. Okay, does that make sense? Remember, when we, so let me, take you back to this fact that we wrote so that this point becomes clear. See, there we are. So we said, hey, you know what? Let's say lambda 1 is the maximum eigenvalue of A in magnitude. Then, we could take this, a trace of high power, especially high even power, and, do all this L infinity to LP trick, right? But this really required that the distinguisher we are using is the eigenvalue of maximum magnitude, not the maximum eigenvalue itself. Like in other words, the sign of the eigenvalue, it was important that we ignored the sign of the eigenvalues of A when we dealt with the spectral algorithm that we saw today. It was okay for the examples that we were dealing with because, the maximum eigenvalue also happened to be the maximum magnitude eigenvalue for the examples that we discussed. But it turns out that this lambda max that appears in this statement of the proof that I showed you the last time, statement of the claim that I showed you the last time, is really truly lambda max. It's the largest positive eigenvalue. And, yeah, so in some sense, a natural approach might be to improve this connection to spectral algorithm that I showed you last time to replace lambda max by, the largest eigenvalue in magnitude, which is equal to the spectral norm of A. So instead of lambda max, if you had spectral norm of A, then you would be able to simply use our L infinity LP trick and complete the proof. Now this seemingly technical problems is actually somewhat major, so the approaches that we were trying actually didn't go through. But yeah, so like the theorem that I showed you, like in summary, like the theorem that I showed you last time, which showed the equivalence between SOS and spectral algorithms, was really proven on the way to actually approach the pseudo calibration conjecture. We did not manage to prove that because the gap between lambda max and maximum maximum magnitude eigenvalue of A, which is equal to the spectral norm of A. So um, gap between does that answer your question?
Yeah, thanks.
Yeah. And I don't know if this is the right approach or if this is something you should work on, but some approach that you should push on. But yeah, at least that's the that's the approach we were shooting for earlier.
Oh, I want to clarify. So that conjecture means that low degree or D log n polynomials capture degree D SOS, right?
Yeah. So the pseudo calibration I mean, in both these conjectures, even though I write D versus D log n is a distinction we don't mind. Okay. So if degree D SOS can be simulated by, let's say, n to the D log n size matrices and spectral algorithms, it would have been perfectly okay. And we're not distinguishing between D and D log n here. Like, log n factors would be okay for us here. What we do not know, and what we know is that, that we can actually make this equivalence be true for spectral algorithms. But yeah, for the low degree polynomial distinguishers stuff, we actually do not know. And yeah, so in particular, yeah, does it make sense? You can think of the conjecture as being somewhat loose, as in, like, you can obviously fudge the conclusions by changing D to D log n's if you need, but yeah, those those don't seem to help very much.
Okay, thank you. I have another question if no one
Yeah.
else has. Yeah. So you mentioned there's no stability, right?
Right. Yeah. So I never actually defined what class of problems these are, but these problems, in fact, pose natural restrictions on the distribution D null and D planted. And so one restriction they pose is that if I take a solution, so if you remember, D planted, in both our examples, is a distribution on a planted solution and an instance, right? And so one restriction that the model of large class of average case problems that appears in both these statements poses is that this is well behaved under random restrictions, or let's call it random perturbations. So what does that mean? So if I somehow, for example, let's talk in the context of a click problem. Okay, if I give you a graph G, okay, let's say it has a planted click. Okay, so let's say G is chosen from G n half plus omega click. Now, if I do the following, if I select a subset of vertices, okay, let's say, these are at most n to the 99, okay, and and re-randomize edges that do not go within S, as in, my graph is like this. I preserve n to the 0.99 vertices. I preserve all edges between them as they were under G, but all of these edges I randomize. I just like resample from the D null distribution. Even then, the solution is somewhat preserved. If if the planted click was of size, let's say n to the 0.2, then the n to the point. So this is a n to the 0.99 size set. This, if I choose S, for example, randomly, then it would intersect the planted clique in, some reasonable polynomial number of vertices. And so, even after re-randomization, this graph would continue to have a large planted clique. Okay, so you can think of that as an example of a property where a solution is preserved, as in if an instance is a yes instance, then the property of being yes instance is preserved even if I re-randomize in this particular example sense that I described here. This particular randomization I'm going to call a random perturbation. And so one restriction that holds, that has to hold for, or at least that seems necessary for this conjecture to hold, is that the planted distribution should have this noise stability property, in that if I re-randomize or like noise up the input graph, it still remains a planted instance, perhaps with a decreased whatever size click or whatever, but it still remains a yes instance after re-randomization. So this is one of the properties that's required, and that's what I meant by noise stability.
Okay, I guess the reason I asked is because okay, Jeff probably knows a lot more than I do, but so like we read some papers about lower bounds for algorithms that are noise stable, and some scores seem to be noise stable, right?
Can you repeat the last sentence?
Oh, so some squares algorithm is robust to noise, I guess.
Okay, so now I understand what you're saying. So I think the intuition is valid here, but the actual noise model and the actual notion of stability really makes a big difference. And in some sense you can think of that, yeah, if I had to use a pithy sentence to end it, like it's all about what is your noise model and what is your stability model. It is, yeah, sum of squares is noise stable, so is low degree polynomials. But under what kind of noise and under what notion of stability is what makes a difference. Now of course we think that morally speaking, all reasonable notions of noise stability should somehow play well with each other, but it's not clear it's true, and even if it's true, it's not clear how to prove it. Like for example, this is, I guess, also I was answering Praneeth's question earlier, which is that, for example, just to give you a sense, so suppose f is a function on, and this is something that you already know, but I just want to make a point of it. Suppose f is a function on R, on the hypercube. Okay. Now imagine the following operation, and this is usually called the noise operator. It does the following: it gives you a new function which at x equals the expectation of the old f on a distribution near x. So in some sense what this does is it takes, at any point x, it takes the input, and then flips every coordinate of this n row of x distribution, flips every coordinate of x with probability like 1 minus rho. Okay. And so you get a distribution on y's which are somehow near x in this. Now average f over all those y's. Okay. So this is a particular way to noise up f, right? You're taking f, and at any point x, you're like averaging over like some small ball around it. That's what you're doing, right? Now here is a property. You can ask, what is the correlation of t rho fx with fx? So if I randomly pick x from +1 minus 1 to the n, what is the expectation of the product of fx with t rho fx? In some sense, think of this as a question of how close is f after noising. Okay. And so you can think of this as a natural notion of stability, right? If my function was extremely noise stable, then it would not change after after I noise it up, which means that in some sense the correlation will be the highest possible correlation, right? Still good? Still makes sense, Tim? So, in particular, this quantity can never be more than expectation of T rho F squared, expectation of F squared by our favorite inequality. And, if it is near that bound, we would say that F is stable. Yeah. So it turns out that in this notion, F is noise stable if and only if F is well approximated in L2. So actually, let me write in if and only if there exists a G low degree polynomial such that expectation over the uniform distribution of F minus G square is small. Now again, I'm not writing the parameters, etc. here, but the degree of the polynomial depends on this epsilon and the noise rate rho, whatever. But this is the definition under which noise stability is simply equivalent to being a low degree polynomial, right? So if you were to define a class of algorithms which satisfy noise and stability in the notions we discussed here, then you will truly end up with a low degree polynomial method as the right algorithm, because simply that's exactly what they correspond to. But you could come up with a different notion of noising. In particular, this kind of noising where I took a subset of vertices and then randomized the edges. It does not correspond to the kind of noising that we did here. And then I could be interested in a different kind of stability. In particular, in the click, I was interested in the stability of the solution. And then it's not clear what algorithms would arise. Okay. Anyway, so this was like some simple illustration for why both the notions of noise and stability matter. Does that make sense?
Wait, this notion of stability is equivalent to low degree.
Yeah, it is literally equivalent.
Is this obvious to see?
No, it's not obvious to see. It's it's also not very hard, but it's a somewhat basic theorem in Boolean Fourier analysis.
Okay.
So check out Ryan's book. Yeah, but you can try to, like, I think in some sense proving it is not so hard either. So yeah, okay. So in some sense the proof basically involves the observation that you can write down the Fourier transform of T rho F completely in terms of the Fourier transform of F. That's maybe the main observation. So T rho F hat at S is, if I remember correctly, it's 1 minus rho to the size of S, F hat S. I might be messing up some constants, but you exactly know, so basically every Fourier coefficient of T rho F is basically scaled Fourier coefficient of F. And the scaling depends on the noise rate and is exponentially falling in the size of the set S. So you can like completely compute, these correlations. And then, because these are exponentially decaying, you can show that, the terms in the tail cannot really contribute too much. And so if the noise, if the function is really stable, then it better be that the Fourier coefficient which were large did not contribute much. And then, that's literally the definition of what F being approximated by low degree polynomial means. Anyway, but you can make this discussion into a proof with like 15 minutes of work. So it's not so hard, but also, you can find a proof in Ryan's book.
Okay, thank you.
Yeah.